In this video, we'll be discussing the finer points of using the road force balancer to achieve low drivability harmonics at high vehicle speeds. Cut! What are you doing? Huh? This isn't that video. I told you which one this was 2 minutes ago. 2 minutes! You can't remember something from 2 minutes ago? I can't keep working under these conditions. They call the people in front of the camera the talent. It's the people behind the camera that are the real talent. Oh, I'd fire you if I could, but the union would have such a fit they'd come down on me so hard after that last time. I swear, I don't get paid enough for this. And you know what else? You know what else?
What?
Recorded from my garage. It's fuel pump speed calculations. We're going to be talking about how to calculate the fuel pump speed and amperage. This is something useful for diagnosing fuel systems. And I'll give you some examples a little bit later in the video about where we'd actually use this and what it's going to tell us. And in just a second, we're going to go over to a waveform and I'll show you exactly how to measure off for the calculation. But before we go there, I want to give you the calculation really quickly. Yeah, sorry, more math. A little algebra this time. First off, we need to know, since we're looking for RPM, how many milliseconds in a minute, and that would be 60,000. The next piece of information that we'll need is the number of milliseconds it takes the fuel pump to make one rotation or revolution. Again, I'll teach you how to do that in just a minute. Then, what we're going to do is divide that. So, if we had 10 milliseconds for one revolution, we would divide 60,000 by 10 milliseconds. That would give us an RPM of 6,000. Our fuel pumps typically run around 6,000 to 7,000 RPM, and they can draw anywhere from 3 to upwards of 12 amps. A more normal range would be roughly 5 to 10 amps and 6,000 to 7,000 RPM, but like a lot of things, it depends. So with that, let's go take a look at how we're actually going to find the number that we need to calculate this, and we'll double check our amperage at the same time. We're going to use this waveform and go over a quick tutorial on how we're going to calculate the fuel pump speed and take a look at the amperage at the same time. This particular case was taken off of my Expedition. See one of the previous videos. First off, what we have to do is identify how many commutators this has and measure the time. We're not going to do it like this, so we're going to need to zoom in. So I'm going to pick a fairly small window here. All right, that's actually not a bad capture. You'll find the closer you zoom in, the better detail you'll have, the easier it's going to be to pick out your commutators. But now I'm going to look and see if I can identify something that's kind of similar as we go through here. See if I can pick out something that makes it easy to see. Let's see here. I have this right there, and 1, 2, 3, 4, 5, 6, 7, 8, and there it is again. Let's see here. Oh, look at this. I have these couple here that have, it's a lot flatter on this low end. 1, 2, 3, 4, 5, 6, 7, 8. All right, there. See how familiar that and the following one look, along with that and the following one? So for clarity, I'm going to pick that following one. You can see it's kind of flattened with a little jagged edge. Flattened with a little jagged edge. So I'm going to put a cursor right through the middle of that. I'm going to grab my second cursor and I'm going to bring it on the next one. Okay, you see how similar not only that this one and this one are, but the ones before and after also happen to match. So if we look here, We have 1, 2, 3, 4, 5, 6, 7, 8 peaks in between the two. Now I set my cursors up so I see my 8 peaks occurred in we'll call it 7.7 milliseconds. Also, I want to know what my amperage was. So I'm going to pull my cursor down and I'm just going to put this line, just kind of center it through that waveform. And I'm going to see that I'm pulling about 6.7 amps. So about 7 amps, perfectly normal. No worries there. 7.7 milliseconds. So my calculation, I'm going to take 60,000 because that is the number of milliseconds in a minute. I'm going to divide that by my 7.719. That was this number up here. And that's going to give me 7,773 RPM. Now, I said that around 6,000-ish was pretty normal. You know, I'm not going to get too excited that this thing's spinning 7,700. The vehicle wasn't being driven right now. It was under low demand. The amperage is normal. And I wasn't really going for a problem. So this isn't really all that strange. I'm pretty happy with 7,700 RPM. So we're going to look for something common in the waveform, a repeating pattern on which we can line up our cursors. And when we find that and set up our cursors, then we count the number, because we should have typically 8, 10, or 12 of these bars or humps in here. And then we're going to see how much time was between them, my delta box up here in my cursors, and we're going to divide 60,000 by that number to give us our RPM. I'm going to throw a couple scenarios at you real quick, just so you get an idea of how we're going to use this. Now, normally, we would see a speed of about 6,000 RPM. And we're going to see an amperage, depending on the pump design, of 5 to 10 amps. So these are our ballpark numbers. Now, depending on pump design, depending on era of car, these change, right? These are a rule of thumb. If we get too far outside of this, well, then we check our known good if we don't already have it for the vehicle. But a couple of potential problems here I'll show you. What if we have 10,000 RPM and 3 to 4 amps? So on a vehicle that would normally be about 6,000 RPM and 5 to 10 amps, we hook up and we've got 10,000 RPM and only 3 to 4 amps. So what we're saying is the pump is spinning really fast and it's not consuming or utilizing a lot of current. So that tells us that pump's not really working very hard. The high speed, low current, it's not doing much work. And the most common cause of this? Yep, no fuel in the tank. How about this one? Now we have a really low RPM with a really high current draw. Now we're looking at something that's making that pump work very hard. It's drawing a lot of current and it can't spin very fast. This thing is doing some work. In this particular instance, the most common cause? That's often a plugged fuel filter. Plain and simple. Then we have one more scenario I'll throw at you. There are different things that can happen. I'm just throwing a couple at you. We'll throw one more. So we've got 4,000 RPM and about 4 amps. So this really isn't working all that hard, but it also isn't spinning all that fast. It's not utilizing its power. It's not spinning. It's not drawing a lot of current. In this instance, now we're likely looking at either just a plain worn out fuel pump, it's just old, it can't do the work anymore, or we have high resistance somewhere in the electrical part of the circuit that would have enough of a drop in voltage, we're not able to get enough power to the pump, so we're dropping our amperage because we have too much resistance somewhere else, and since we can't get enough amperage down there, we see the RPM drop, and our pump output goes down. So hopefully you can utilize this, or at least use this to help you understand why we might look at going to the trouble of figuring out a fuel pump speed and current to do some testing. Now, to end this video, I'm going to bring you a tale from the shop. A good example of how utilizing fuel pump waveform, looking at the fuel pump speed, fuel pump current, led me to a quick diagnosis. So the day started out simply enough. We're working away in the shop, look down the street, notice an old green Volvo coming up on the tow truck. After winning a quick game of not it, I didn't end up working on it the first time. Car came in for a no start. One of the other technicians checked it out, found that it had fuel pump problems. I was off doing something else. Customer was called, parts were hung on the car leaves. Less than a week later, here comes the tow truck down the street, green Volvo on the back. This time, not it didn't work for me. So, I go to the car. I have no fuel pressure at the fuel rail. I don't have enough fuel to start the car. I check in with the technician that worked on it. Well, it came in with no fuel pressure, no fuel at the car. He tested it. He found that the primary fuel pump had failed. Now, I should note that this car has two fuel pumps. It has a transfer pump back in the fuel tank, and it's a low pressure, high volume pump, so it can move a lot of fuel. It just doesn't do it at a very high pressure. And that feeds the high pressure pump that's outside of the fuel tank. Now that high pressure fuel pump ramps the pressure up, sends it up to the fuel rail for injection. So I check with him. I said, well, you did both fuel pumps, right? Because what normally happens is the pump in the tank, the transfer pump, usually dies. And then that means that the high pressure pump has to work too hard. Nope, the customer didn't have the money for it. Well, you put a filter on it, right? You should always replace fuel filters. Any fuel pump replacement, you put a fuel filter on. It's cheap insurance. It's just a good idea. No, the customer couldn't afford that either. So the only thing you put on there was the single high pressure pump. Yep. Okay. Well, not a good day. All right. I take my lab scope, I connect it up, I get a fuel pump reading. I figure out my fuel pump RPM. It's spinning somewhere between 35 and 4,000 RPM when it should be well over 6,000 RPM on this car. I have a situation where my current draw is very high, 12 to 14 amps, much higher than it should be on this car. Now I'm testing the high pressure pump. So now I know, because I have low RPM and I have high current draw, I have a restriction somewhere past that pump. That usually means I have either a restriction in the fuel filter or I have a fuel pressure regulator that's stuck shut. Now, since the fuel filter didn't get changed on the job, that's the first place I went. It's easy to get to, and fuel filter tests are simple. You blow through the fuel filter and you see if it blows through clearly, you know it's okay. If it's difficult to blow through or it takes effort to blow through it, if that's the case, then your fuel filter is restricted. But now, mind you, I'm not happy right now. I didn't want to work on the car. I still don't want to be working on the car. And the car is probably back and I'm working on it simply because the processes that we have in place to repair these cars properly were not followed. So I'm upset, not thinking clearly. I pull the fuel filter out. And of course, I go to blow through my fuel filter. But remember, I'm not happy, so I'm not thinking straight. And I get a face full of fuel. So, the fuel filter's plugged up, simply needs to have a fuel filter replacement, and that ended up fixing our Volvo. Had they simply followed the proper procedures, it would have taken care of the car in the first place and it wouldn't have been back on the hook. So that's an excellent place to utilize and trust your tests. In this case, the simple weight of the fuel filter, how heavy it was, actually already told me how restricted it was. My blow-through test was just the icing on the cake. And with that, we'll catch you in the next video.